this example, the loading status of the beam is given as follows, and we're looking for the internal forces at point C. To find the internal forces, first we need to figure out the external support reactions. So in this case, we have support at A and at B, but since we're looking for the internal forces at C, and we're going to use the method of sections where we're going to run the imaginary cut through this point C. And we only need to choose one segment, the left segment or the right segment, to find the internal forces at point C. So in this case, we don't have to solve for all the support reactions. We just need to solve for the support reaction at A or at B. And in this case, I would choose support reaction at A since there's only one support at A, which is AY. There are two supports at B, BX and BY. So we want to choose the segment with less number of forces. So the left segment is what we are going to do. So this is the quick analysis. First, let's determine the external support reaction. To find the external support reaction, first we need to draw the free body diagram of the entire frame. This is point A and this is point B. We're going to place all the external forces on this beam and also removing all the supports, the ball support at A and the pin support at B. So this is my free body diagram with all the applied forces, and also I reduced the distributed load with one concentrated load. So again, since we're going to choose the left segment to calculate for the internal reactions at C, so we only need to find the FA. I'm going to use the moment about B to find the FA. And that's the equation. And FA is solved to be 302 pound-force. Step 2, we're going to run an imaginary cut through the point where we are looking for the internal forces at. In this case, will be the point C. So we're going to run the cut through point C and choose the segment that we're going to analyze, which will be the left segment. So here, keep in mind that the distributed load and the couple moment must be kept in their original positions until after the section is made and the appropriate segment is located. So just leave everything as they are now. Do not move anything. So draw the free body diagram of the left segment. This is point A and point C, and also don't forget to set up the X and Y axis. At point A, we already solved the FA, so we can use it as a given value. This is 302 pound-force, and over AC segment, here is the distributed load. So for now, I'm going to just leave the distributed load over here. So you know this is the left segment, and I'm going to reduce the distributed load to one concentrated load just in a little bit. And this segment has a length of 2 feet. Okay, so those are the only applied forces on this left segment. So we are gonna notify the internal forces, but now they become externals, right? Based on the sign convention, there is a normal force which will be perpendicular to the cross-sectional area, and we assume it is a positive normal, and C, which means is a tensile. And the next one is along the y direction, which is the shear force. Based on the sign convention, the positive shear force will cause a clockwise rotation for this left segment. So VC, this is the positive VC direction. And the last one will be the bending moment. So upwards, concave upwards bending will be the positive bending moment at point C. So that's everything we have. Apply the forces and the unknown forces, which are the internals, becomes externals. So now we can reduce this distributed load to one constant to the load to help us write down the equations, equilibrium equations. So this is the force pointing down, 80 times 2, which is 1 foot from point C and also 1 foot from point A. And we have 3 unknowns, and this is a 2D rigid body equilibrium problem. So we can write 3 equilibrium equations to solve all of them. First equation will be sum of Fx equal to 0, since there is no other force in the x direction, so the NC should be equal to 0. Next equation, sum of Fy equals to 0. Now we can see the VC actually is the sum of the y direction forces from this Fy equals to 0 equation. So we have 302 minus 160, which is 80 times 2, minus VC equals to 0. So we can solve VC here, which is 142 pound force. And the last equation will be the moment about point C. The reason I'm choosing point C is because we want to find MC, but we don't want to have VC and NC in this equation. So that's why we choose MC. So it's negative 302 times 2 feet plus 80 times 2, which is 160, times 1 foot plus MC equals to 0. And from this equation, we can have MC, which will be 444 pound-foot. And this problem is solved. Let's see another example. In this example, we also have a beam very similar to the previous example, and we're looking for the internal forces at point C. The only difference is point C is not directly under this distributed load. Instead, there's nothing happens at point C, looks like. So we're going to follow the procedures using the method of sections again to section at this point C. And choose the segment, right, left or right segment. And in this case, we are going to choose the right section because right section is simpler, doesn't have any distributed load. We only need to figure out the support reaction at pin B. Then that's it. So the internal reactions at C totally depend on this support reaction at pin B. So first, we need to find By, the support reaction at pin B, and also Bx if there is a Bx. So we're going to use the free body diagram of the entire frame to find the support reactions for the frame. Even if we don't need to find AY, we still need to place AY on the free body diagram, because for a free body diagram, you should have all external reactions, external forces on this free body diagram. Otherwise, your equations of equilibrium will be wrong. And here I replace the distributed load with one constant to the load. 6 feet times 3 kip per foot, so which will give us 18 kip. And at point A, we have AY, and B, we have BX and BY. 3 unknowns, and we can write 3 equations. Again, we don't need to solve for AY, we only need BX and BY. So BX is 0 because that's the only X direction force. And from this equilibrium equation, it must be 0. And BY can be calculated using the moment about A. Again, we don't need the support reaction at point A, we only need point B. So if we use moment about point A, we can solve BY, which is 6 kip, kilopound force. And now we can draw the free body diagram of the right section and assume the directions for the shear force, the normal force, and the bending moment. So the right segment starts from point C to point B. And at point B, there's only one reaction, which is BY. And at C, we place the internal forces here. And in this case, you can see this NC is drawn as a compression. It's pushing into this member CB. But it doesn't really matter because NC is the only force in the X direction. It will be 0 anyways. So write 3 equilibrium equations to solve for the unknowns. NC is 0, VC is negative 6 kip, and MC is negative 27 kip foot. So the negative sign indicates that VC acts in the opposite sense to that shown on the free body diagram. So it should be a shear force going up instead of going down. Same idea for this MC is bending downwards instead of upward.